I want to define what we call a transpose. The transpose of a vector. Okay, so could you guess what we're going to start with? Yeah, so in this case, what is the main type of vector that we focused on thus far? And I forget your name. Yeah, behind you, the gentleman. Chris, yeah. What's the main type of vector that we focused on so far, Chris?
Column vector.
Column vector. So maybe we'll start with a column vector. We define the transpose of x to be the 1 by n row vector x transpose. This is not read x to the t. And we'll talk more about that in a second. This is not x raised to the exponent of t. This whole thing is read as x transpose. And let me be clear, if x was n by 1, how big is x transpose? 1 by n. And this is kind of interesting. You could write x n by 1 transpose. So before I've taken the transpose, how big is it? N by 1. Then I take the transpose, how big is it? 1 by n. Which means if I take x1, x2, all the way down to xn transpose, what happens? x1, x2, xn. In other words, the rows go to columns. Okay? So rows turn into columns. Could you guess what we say about the transpose of a row vector? Yeah, so let's go ahead and take a look at this. So let's suppose y is an element, instead of a column vector, let's turn it into a row vector. Then y 1 by n transpose. Well, once we've taken the transpose, what happens? All the rows turns into columns, and the columns turn into rows. So this would be y1, y2, all the way to yn transpose. And what does that thing look like? Column vector y1, y2, all the way down to yn. This thing had 1 row and n columns. The transpose has n row and 1 column. Claim, I meant to say this, theorem 5 can be restated completely for row vectors. That would be a fun exercise for you to do in your free time. To restate all of those operations in the space of row vectors, right? The last thing we're going to do before we actually take a break is we're going to look at some algebraic properties of transpose. Or did I promise you a break already?
Like 3 things ago.
3 times? Okay, so you want to take a break now?
No.
Yeah.
I want to finish this. That's one of my...
Keep going.
Should we keep going?
Yeah.
Okay. How about this? I don't announce breaks from now on. I'll keep you on the edge of your seat. No? Yeah. Thank you, thank you, thank you. Never stop laughing, especially at me, my ugly mug. All right, of vector transposes. All right, so let's look at this one. So let's let x be an element of Rn. And I suppose we actually need 2 vectors. So maybe in this case we'll let x and y be an element of Rn. Could you guess what happens if I take the transpose of the transpose?
It equals x.
It equals x. So the first thing I would do is I would turn a column vector into a row vector. Then I would turn that row vector back into a column vector. So it must be back to the same thing, right? Okay. What if I were to take x plus y and then transpose it? Yeah, that would be equivalent of first taking X transpose and then adding that to Y transpose. This would be row vector addition. This would be column vector addition, right? Okay. And then could you imagine what happens if I go A times X transpose? Yeah, this is scalar column vector multiplication. Yeah, and this now turns into scalar row vector. Okay. I leave the proofs of those to your break time. Say it again? No, I guess I'm trying to say when the transpose is a unary operation, right? The transpose expects one argument inside. And so if I just write A times X transpose, we haven't really talked about order of operations for unary operations, right? We haven't said, like, do I first multiply scalar multiplication and then take the transpose? And what I'm saying here is, in this case, we're first associating the scalar multiplication, so this is a scalar column vector multiplication. In this case, this is a scalar row vector multiplication because the transpose has happened first. So I'm like forcing us to say transpose happens first because parentheses happen first, right? Yeah. All right, ready? Break.